Welcome everybody. My name is Bianca. I'm a geologist at the University of Göttingen, and I will share my talk with my colleague Claudia. So both of us will show you two kinds of deliverables we created in Work Package 7. And up to now, I think you heard most of the results from the other work packages, but Work Package 7 is dedicated to the assessment and especially to the distribution and upscaling of the meet results. And the other talk will be given by our colleagues from Croatia. So it's not just me and Claudia, there are other colleagues. They are listed here on this first slide. So it's a cooperation between the Geoscience Center, our state and university library, and the Institute of Computer Science of Göttingen. So it's always a team. So in our task of Work Package 7, so there are 3 tasks, and we created this of task number 3. There are more than these 2 deliverables we will show you. There are several potential maps. There's a list of potential sites, and there are also the data management plans in various versions. And all of these other deliverables will be available on the Meet homepage and in our Zenodo community. But today I'm focusing on this one and my colleague on this one. So deliverable 7.8. So the original or the first name was a catalog of relevant spatial data sets for further geographical analysis. And later on we changed to database because we realized now a catalog is not efficient enough to really bring the information we want to provide to you in a good and handy way. So what was our starting point and what was our main objective? So first of all, we were focusing on geodata because our colleagues, especially in the other technical and scientific work packages, were dealing with a lot of data, and a lot of this data are connected to some kind of location. So these are geospatial or locational data. And it would be good for other geothermal projects not to go back to the original same starting point we had. It would be much better to go some steps forward and start where we left off. So, but what would be a good way to bring some of our experience to you? So, and in this multidisciplinary project, there are so many experts, you heard already some of them, and there's so much experience, and we are dealing with a lot of methods. And then we realized it's not just about data, it's more about the methods and the data, because they belong together. And if you want to use some data, it's always good to understand, yes, what kind of methods were used to create this data, or what data do I need for the next method. So, and if I connect parameters and methods and data, I create workflows. And we then decide we would like to look for a way to make them reusable for you. On the lower right side, this is a schema of our Meet project. So the technical work packages are 3, 4, 5, 6. I'm talking about 7. And then there are some more administrative and public relation related work packages here. And in the larger picture, there's also a very general scheme. For instance, what was done in Work Package 5. And you see there are several scales, outcrop area to reservoir scale. And there are a lot of different methods, and there are connections, and there are parameters. So this is one example of some kind of workflows we were dealing with. And in the upper left side, the other work packages are mentioned, and all this is implemented into Work Package 7. So there are a lot of connections between these different steps. So, but what would be a good way to map this kind of complex system this project is? So, as I told you, the starting point was geodata, and these are in some kind connected to methods, parameters, and also to literature, because we are really trying to address open science and fair principles, and it's always the first rule, to mention your citation or to cite your sources and mention your literature. In the background is a little bit transparent. This is the first scheme we created to really try to map this network-like information. And then we realized we started with a PostgreSQL database made up of several tables, and this would be not the best way to really map this kind of network. And that's why we had to change our concept from table-like structures to more network-like structures. And maybe you already heard about this graph concept, so graph databases. And the core concept is the smallest unit or the smallest element is one information, one node is connected to another one. And this could, in software terms, it's called one instance, has an object property and is so connected to another instance. And in our database examples, it would be one parameter is described by a geodata set or some kind of geodata. And this approach is used for some years now in all the scientific community. Maybe you are using Semantic Scholar or some kind of Wikidata. This is the concept using this network-like connections of information. So, and beside these nodes and instances, there's another core element. These are classes, and these are more like drawers, and we can put all this information in several drawers. And our 6 main drawers are, for instance, of course, geodata, methods, parameters, literature, objects, because most of the geodata or parameter are connected in some kind to objects, to samples, as you saw, or drill cores or scene sections. And the last one, this of course are units and quantities, physical quantities. And luckily, and this is one of the really main advantage of the semantic web, is there are already other databases or so-called ontologies which represent really the most important physical units and quantities. And it was really quite easily for us to implement them into our data structure. So what did we use? We used the open source software Protégé. This was created by the Stanford University. And here you see the graphical user interface. On the lower right side, there's the link for downloading the data. And these drawers I showed you before, the classes, the instances, are hidden or are shown in several windows of this graphical user interface. These classes are organized in a tree-like structure. Maybe if you are using GIS software or other type of data management tools, you might be quite familiar with this. So I have some major classes, geodata, literature, method, and some subclasses. And all the information in one of these drawers is listed down here. This is the real information. These are the instances here in the lower left. And these connections between different kind of instances of information, these lines between these 2 nodes are listed in this, or with this blue sign. This is, for instance, this information comes from the literature Reinecker et al., or Reinecker in 2019. And of course, it's possible to provide some additional description and so on, and this is shown here in green. And this is just the first snapshot how this information, this database information, can be accessed. So another example, if I dig a bit deeper, I jump from general method class into some of the subclasses, and here you find already a lot of the methods we used in MEAT. Here's the abbreviation, or the name is always a bit simplified, and of course every entry has its real name. Here you have the literature source and the connection between these different information types. Here I jump just quite quickly into parameters. So for each method, a lot of parameters are listed. And here we are in the subclass of geodata. Here we have some major data sets which are linked to certain parameters and certain methods, and these parameter data sets are all available, in most cases open source, or there are some special license regulation, but the information is also stored here. There's always a link where you can find this external geodata set. So this database that does not contain measurements or numbers, it contains the information where to find this high valuable information, because I think up to now there are so many different sources of useful data sets. It's more a challenge to find them and to connect them, and this is our approach we show you here. And then we decided, okay, it would be useful to find some kind of visualization or provide some kind of visualization tool. I hope you can see this web application. So my colleagues from the computational geosciences, and Simon is also here today, created this visualization of this graph database. So this is an online tool, open accessible. This is the first view. And here you see some part of this network. And here in the lower, in the middle of this lower part, you have some kind of menu buttons. You can increase the size of the these names, or you can change the orientation of the complete network from top down to left to right, which is much more convenient in most of the cases. And then you can already see some kind of the knowledge we used, we tested, and we created in Meet. So these are some of our workflows. And if I select, for instance, I go to the Syn section, Mosaic 2D fracture trace map digitization. I need to double click, and then I'm able to jump into one part of this really complex network of workflows. And here I have the additional descriptive information, what kind of method is this, and here are the literature sources. And if there would be a data set behind this literature source, it would also be listed. And each of the information is, can be selected and can be searched. So here's another literature source related to the tin section mosaic as an object, which is the input into this method. And from this method, on the right-hand side, I see the other parameters which are created by these tools. On the right-hand side, there's also some kind of menu to shrink the number of or the types of methods you want to use. If you don't want to use some laboratory methods, then you can turn off this selection, and then the number of or the network will be smaller than the original one. So I have to jump back because the time is running. So this is just needs Java and Tomcat, and the description of this, or a short documentation of this visualization tool is also available. So what is this complete database of who could be interested in it? Of course, we are looking for someone who wants to host this database and maybe wants to implement this one in an existing data infrastructure, because this makes much more sense than just to have it somewhere saved. The other one is, of course, who is interested to go further into development and extension, because I think this is a concept which would be really valuable for the geothermal community. And then, of course, it's dedicated for searching and utilizing. It's still a bit experimental, and maybe there could be more data sets in this database, but up to now there's already a lot of information available. And a complete description of all the components and the concepts is described in the Deliverable report, published or submitted for this deliverable. Here you have on this slide the GitLab link, where my colleague Simon already provided the database file and also the visualization tool, and the downloaded description, and also the installation of Java and Tomcat to use. or unique. And the next one, this is the link I already mentioned before. Just to accessing the database, you would need this Prodigy software, which is also implemented or hosted by a really friendly and active user community. So thanks for your attention, and now I will stop sharing my screen and hand over to Claudia, my colleague. So okay, Claudia, the floor is yours.
Yes, can you hear me?
Yeah.
Yes, clearly.
And I hope you can see the slides as well.
Also.
Okay, great. So my name is Claudia MALZER. I actually joined the MEET project only in November to take over the work and finish the work on the web-based map tool. Let's just look at the agenda quickly. So I will first quickly talk about the intention of this web viewer, then give an overview of the system design, and then show you the technical realization. So what features do we have in that web map before I come to the outlook. So in one sentence, one could say that our web-based map viewer developed for the MEET project is intended as a one-stop solution for the wide spectrum of stakeholders that are interested in geothermal exploration and project development. So what do we mean by that? So basically, we can broadly distinguish a geothermal project into surface and subsurface parameters. So on the surface part, we have factors such as the environment, finances, society, decision-making policies, and so on. And on the subsurface part, we have the actual geological factors such as pressure, heat, fluids, rock types, and so on. So currently, the current state is that we actually have a large number of geodata sets and also map viewers, but they are all across the web, and most of them really focus on the geological factors or on very specific parts or specific countries. So our goal was to include a variety of factors. So not only geological factors, but also aspects such as national policies related to geothermal energy, or for example, links to the more specific country-specific viewers. And of course, it should also be easy to enhance depending on the needs of stakeholders. So let's look at the system design. So first, the thematic categorization. So we gathered data in raster and vector format, so in geotiffs and shapefiles, which we later imported into a PostGIS database. We have 8 main categories, which could also be extended in the future, which is a general category: geology, geothermics, hydrogeology, infrastructure, power grid, land and soil, and environment. And each of those categories have at least one or multiple sublayers with the different data. The very basic architecture is divided into 3 tiers. So first we need the data storage part for our different data layers. We then need some way of processing the data and also serving the data as standardized web services. And finally, we have the data presentation tier, which refers to the actual user interface where users can interact with the map and the layers. Regarding the software, we selected open source software. So I guess most of you will know at least some of those logos. For example, GeoServer is quite a widely used software for serving web map services, geospatial layers. Then also OpenLayers is a large open source software for developing web-based maps. PostgreSQL is also open source database. Then we used GeoNetwork for the metadata. And Vue.js is actually a quite modern JavaScript-based platform, which is also easy to extend. Apart from that, we also used Vue.js for pre-processing the data. And all the running services are connected via Docker. Here's another overview of the system architecture. So as I just mentioned, the running services, so basically all of these parts except Vue.js are orchestrated by Docker, which is basically a virtual environment, which allows to very quickly set up or start and stop all the different components. So let's look at the actual implementation. So this is a screenshot of the main user interface. On the left side, we see a sidebar, which in this case, it's already expanded on the geology category. So you can see different sublayers within that category. And we can also already see a legend and some information panels. So let's have a more detailed look on that. So if we look at the, for example, surface lithology layer, if we click on this little button, we can open the legend, which is rendered by the Geo server. By clicking on the information icon, we are forwarded to GeoNetwork, which then gives us information on the metadata, for example, contact persons. We can also bring the layer back or to the front. Of course, we can toggle the visibility of the layer, and we can also adjust the opacity. Then most importantly, of course, we can query the features behind those data layers. So on mouse click, we can view in an information panel what features are behind this location, depending on which layers we have selected, which layers are visible. We also have a variety of map controls. So for example, you have the option to switch between different base maps. You can also search for specific locations. You have a global overview of the map and also a scale bar. Further, you have the option of drawing your own geometries for measuring. So for example, all kind of geometries like point features, rectangulars, polygons. You can also play around with the polygons and cut holes in it. You can draw lines or just use that feature to measure distances. You can also draw circles, and all of these geometries can be imported or exported in GeoJSON format, which is quite a common geospatial data format. You can always go back to one of your features and click on it to find out about the area or the distance it covers. What you can do as well is, if you're interested, for example, which power plants or which geothermal related study programs are in your area, you can select a point and set a buffer around this point to see what features are nearby. Further, via an transactional GeoServer service, you have the option of adding your own company to the layer of geothermal companies and add some information about it. And you have also the option, if you find an interesting data layer somewhere, which is provided as web map service, which is a standardized endpoint, you can also integrate it by just using the link and add it to the map overview. So that was quite quick. Yeah, we already reached the Outlook. So as a quick summary, the European Geothermal Viewer, Map Viewer, includes information about various topics related to geothermal energy and is meant to address the broad spectrum of different stakeholders in geothermal projects. It's based on open source technologies and modern frameworks, which makes it quite easy to extend. And of course, new data layers and categories can be easily added in the future. However, yeah, the open question is who would like to host the web viewer in the future, host and maintain it. So currently there is just basically a demo version on a temporary server. You can find the link here if you're interested in trying out the viewer. And that's it. Yeah, thanks for listening.